Hello and good day. Today in Algebra, we are covering CO7, the final objective of our unit, converting from scientific notation to standard form. And the value of scientific notation comes when you are studying things that are either very, very large or very, very small. For example, did you know that the Earth is 490... Oh, I didn't do this the right way. I'm already not smart. Okay, did you know that the Earth is 491 billion, that's 9 zeros, folks, billion feet from the sun? If you didn't, then you learned something today. Okay, let's write that number again. 491 billion. And again, 491 billion. If you were writing an essay about the distance of the Earth from the sun, you just might have to write 491 billion times, depending on how long your essay is, right? But the point of scientific notation is to take distances or numbers that are used in science, right? That's what science studies, very big and very small things, and just make it in a more user-friendly way to write it, okay? So scientific notation, those that have had an experience with it before, how might you define it?
491 billion, not the 9 zeros.
Okay, so that's kind of how we would write 491 billion in scientific notation, but just a general definition of what scientific notation is. Do we have a sense of that, Peter?
Rewriting it in words?
Not in words, no. There aren't actually any words.
Is it like rewriting it so that the number until it's a whole number and none of the zeros, it's a decimal, and then multiplying it by
Yeah, I mean, oftentimes, this is rounded, by the way. The Earth isn't exactly this many feet from the sun, but with all those zeros there, it's essentially a way to, instead of writing all the zeros, represent them using powers of 10. Okay, so scientific notation is a way to write very large or very small values, and here's the key, using powers of 10. Because what happens to a number whenever you multiply it by 10? What just gets tacked on the end of it? A zero, right? You multiply by 100, you put 2 zeros on it. Multiply by 1,000, you just put 3 zeros on it, okay? So multiplying by powers of 10. I gotta manually delete this mistake up here before I go on. I think that's all I did, okay? So using powers of 10. Ready to practice? Okay.
Yeah.
So Joey kind of started to explain it here. How would you write 491 billion using scientific notation? Go ahead. Yeah.
4.91 times 10 to the 9th power.
Right. So instead of all these zeros, there being 9 zeros there, okay? Another way to write 9 zeros is to simply put times 10 to the 9th power, right? Because that exponent means you're taking 10 times 10 times 10 times 10 times 10 times 10 times 10. And if you're doing it 9 times, you get those 9 zeros. I should have told you not to write this down yet because we're not quite done yet. Okay, sorry. But the other piece of this is that in order to be in scientific notation, we have to have one number to the left of the decimal point. Okay, we actually write this as a decimal, and there can only be one number to the left of it. So we got this 9 from our 9 zeros, because we moved 2 more numbers over, the 1 and the 9, that's a total of 11 placeholders we need to account for. The 9, the 1, and then the 9 zeros. So scientific notation, you can write this down now, would be 4.91 times 10 to the 11th power. Okay? All those zeros, and then those 2 non-zero digits that we had to move over as well. Yeah?
Why do we have to make them that?
Because, first of all, to let you know that it's in scientific notation, right? And then also, just so it's kind of standard, you know, this 11 tells us that we're moving this decimal over 11 times, 2 times to get back to 491, and then our 9 zeros that come after it. Okay? Because whenever you multiply by 10, you're moving the decimal point over to the right. Whenever you're dividing by 10, you're moving it to the left. You know, that's why 36 divided by 10 equals 3.6. You know, you're dividing by 10, so you move that decimal over once to the left. Okay, so decimal point is there to show that we're multiplying by 10 11 times. There's 11 movements, 11 placeholders that need to be accounted for. Down to practice a little bit. Rewrite in scientific notation 5,670,000. All these zeros we get to eliminate. Okay, we have to keep the non-zero digits though. That 5, that 6, and that 7. That gets written as a decimal, 5.67. And how many times would we have to move that decimal over to the right to get back to 5,670,000? At least 4, right? Because we had 4 zeros there, plus, Joe, total of 6, right? So 5.67 times 10 to the 6th. You will rarely see me use the x to represent that we are multiplying. I usually use parentheses or the dot. However, part of scientific notation is that we do use that x. Okay? So 5.67 times 10 to the 6th power. How about 878 trillion? Oh my, 878 trillion. We have 12 zeros that we're able to eliminate. The decimal goes between that 8 and 7, so 8.78 times 10 to the what power? 14th power. Okay. Sometimes when you do really large calculations on your calculator, it'll put the E on the end of it. That's what the scientific notation is representing here. Okay. So your calculator can do it too. What about if we're talking about something really, really small? Okay. In this case, we still want to get that decimal between the 1 and the 3 there. And we have to move it 1, 2, 3, 4 times to get there. But when we write this in scientific notation, what do you think we have to do to the exponent to identify that the number is actually really small? Caleb? Yeah. A negative power, 10 to the negative 4th, means that we're moving that decimal to the left. So that if you saw this number, you would know 1.3 times 10 to the negative 4th, I've got to move this over 1, 2, 3, 4 times. Fill all those placeholders in with zeros. Whew, that's really small. Okay? So a positive power, big number. Negative power, small number. Okay? 4.901. That 0 is included because it's in between two non-zero numbers. 4.901. How many times do I have to move the decimal to get there from where it's currently at? 7. 1, 2, 3, 4, 5, 6, 7. Okay? And because we started with a small number, I mean I have to move that decimal back to the left to get there, get back to it, it's times 10 to the negative 7th. So why is the exponent positive? Okay. Big number, right? You have to move the decimal to the right to get back to your original number in standard form. Okay. Why is the exponent negative? Small number, right? You have to move the decimal left. A positive exponent means you're multiplying by 10 over and over again, powers of 10. A negative exponent means you're dividing by 10, right? Over and over again to move that decimal point left. So the bottom section here, where it says rewrite in standard form, 7.613 times 10 to the fourth, which direction am I moving the decimal point? Right or left? To the right. And how many times? Adam? 4. So 7.61 or 613, moving it to the right 4 times. 1, 2, 3, 4. What goes in that extra place value? A 0. And so my original number was actually 76,130. Probably just easier to write that one as 76,130, but so we have it. Got to teach you something. Yeah, there you go. 6.8 times 10 to the 10th. 6.8 times 10 to the 10th. Which direction is the decimal point moving? Blake? It's a positive power. Positive power means our number is big, so we have to move it to the right. We're multiplying by 10 over and over again here. So our decimal point will go to the right. We move it 10 times. How many zeros does that bring us to? We can kind of start to do some of this mentally, right? If one movement gets us to the other side of that 8, how many movements do we have left to go? 9, right? So how many zeros how many zeros end up being added here? 9. So 6, then an 8, and then our 9 zeros. Throw some commas in there. 68 billion. Big number. Okay. 5.1973 times 10 to the negative 7th. Look at that exponent. Negative 7. Which direction is the decimal point being moved? Drew says to the left. Drew is right. How many times do we move it? A lot. More specifically? 7 times. Okay. So I'll kind of do it up here. 1, 2, 3, 4, 5, 6, 7. We get to fill all these little holes here with zeros. Okay, so our original number was 0.12345651973. Woo! That's small. All right? That's small. And we know it's going to be that small because that exponent's negative. Okay? The decimal point gets moved to the left. 8.21 times 10 to the negative second. 8.21 times 10 to the negative second. Negative exponent, we're moving it left. 2 times. 1, 2. 0 in front. 1 0 filled in. And 0.0821 is our answer. Questions on scientific notation? Again, basically used to write very large, very small numbers in a little bit more concise way. Your homework is, I believe there's a second side to this. Yes, rewrite in scientific notation. You've got 8 of them to do there. They're written in standard form. You need to write them in scientific notation. Then rewrite in standard form. And then at the very bottom there, we have our first nifty tidbit, fun fact. At the time of this document's last edit, I was about 1.133 times 10 to the 9th seconds old. How many days is that? Yeah. When I last edited this page, I was 1.133 times 10 to the 9th seconds old. What's that?
Were you counting?
I have my ways. How many days old does that equate to? Less than 5 million. How old do you think I am?
Older than your 36.
Okay. Yes, 36 years, but that may not have when I didn't edit this on my birthday. So,
28 days.
yeah.
5 seconds.
All right, that is your homework for tomorrow. When we're done going over this, you'll get your practice test and then your actual test. Your test for realsies will be on Friday. Con is due tomorrow as well, so if you have a busy evening tomorrow night, you might want to get that done tonight. And you just got your new math packet, so that's 3 weeks out. That, folks, is How You Math.
Don't forget